Welcome back, everyone. I want to continue our discussion on programming the PLC. Let's review some of the concepts that we learned in the last lecture. First, each screw terminal on the input module, each one is represented by a unique address, and we can map that address to an instruction that you would use to program the PLC. The symbol for any input is a contact, and we looked at two. We looked at what looked like a normally open and a normally closed contact, and we called the normally open contact the examine if closed contact, and we called the normally closed contact the examine if open contact. And we looked at those in the last video, and we looked at when each of those instructions is true and when each instruction is false, so you want to make sure that you're clear on that. So the symbol for any input is a contact, examine if open or examine if closed, and the symbol for any output is a coil. What I want to talk about today is how does that program look in memory, and how does it interact with memory, and what are the different parts of memory. You know from previous discussions that the memory is one of the main sections of the PLC that you were told to remember, and this is why we want to talk about how the program behaves in memory. So this term, processor memory organization, turns out to be important to helping you to understand your program and how your program interacts in memory. So we'll talk about how memory is organized, and not all PLC manufacturers organize memory the same way. So the idea here is just to kind of get a general feel for how memory could be organized, and we'll look at a specific layout for our memory organization, but it could be different depending on the PLC that you use. When I mention or talk about memory organization, I'll use the term memory mapping or memory map. So here's the definition. A memory map shows how memory is organized, and then, as I said before, every PLC has a memory map, but it may not look like the one illustrated below. For our class, we're going to think of memory like this. We'll think of memory as having three main sections: the data table section, the user program section, and then this housekeeping memory, which it kind of runs in the background, so we never interact with that. But you as a user, the user program causes the controller to operate in a particular manner. This is the logic that you enter. And then the data tables, well, we've already talked about two main data tables, the input image table and the output image table, but you'll also learn about some other data tables. So any data table, any storage of the binary zeros and ones that represent the state of a switch, a contact, coil, or any other kind of data from the outside world will be stored here in the data table section. This next slide shows a more detailed view of memory map, and you can't really see it. Let me move this down, but this is for Allen-Bradley PLCs. So it says Allen-Bradley uses octo. You might see here the number system looks a little weird, but if you remember octo base 8, so we go from 00 to 7. There is no 8, and if you look at these numbers, you'll see we're counting in octo. But the point here is that we have these different areas in memory, and realize that memory is not structured like this or like this. This is just a way to think about it. So this is a logical way for us to think about it. So we have these areas here, and then each area has a address, so we can actually narrow it down to the specific cell or group of cells that we're using for a particular work area. So we have these different areas: processor work area, output image table file, bit word storage, and so forth. So you can kind of look at that and get an idea. You can see that it can be somewhat complicated if you actually look at a more detailed memory map. So remember, we'll use this version of a memory map So we want to talk about the data table section and the user program section of memory. So let's look at user program section of memory. And the user program is where the program ladder logic is stored. So you create a ladder program, you save it, it goes to the user program section of memory. So most of the memory will be used by programs that the user puts in. Data table section of memory. Now we've actually talked about, as I mentioned before, the input image table and the output image table. So if you refer to that handout or that slide when we talked about those, I told you to think about just a bunch of cells like an Excel spreadsheet, and those cells have to contain the value whether you put it there or not. You cannot have an empty cell in the table. It has to contain a 0 or 1. If you put the information there, if you put the 0 or 1 there, we call it data. If it was there already and you're going to write over it with something else, it's called garbage or trash. But every cell has to contain something. And so we mentioned, as I said, the input image table, which shows the status of a switch. If I have a switch that's open, then in that particular cell that switch is mapped to from the address or by the address, if the switch is open, that cell will contain a 0. If the switch is closed, that cell will contain a 1. Well, we'll talk about other devices. We can have timers, and we'll talk about timers later on. You'll do a lab that involves timers, and counters, and you'll do labs that involve counters. But these are other types of devices, timers and counters, and any other device. It would also store data in the data table section of memory. Now, timers and counters specifically are more complicated devices, and what I mean by that is you can represent the state of a switch with 1 bit, because the switch is either open or closed. If a switch is open, the openness of that switch could be represented by a 0. If a switch is closed, the fact that the switch is closed, we can use a 1 to represent the closed switch. But a timer or a counter, there's more things that we have to consider. There's more parts to a mechanical timer, so you would expect, if I'm going to have a virtual counter, the logic to represent that virtual timer or counter would be more involved. So it takes more than 1 bit to represent a counter, and it takes more than 1 bit to represent a timer. And we'll actually go into the details of counters and timers at a later date, so I don't want to go into it now. But just suffice it to say that for each of those virtual devices, yes, you have to actually use whole words, several words of memory put together to store the information that you would need to reflect a timer or counter in memory. And so it takes more room. And so these tables for counters and the table for a timer, those data tables are a little bit more involved. They're more word oriented instead of bit oriented. So data tables store information needed to carry out the user program. This includes the status of I/O devices, timers, counters, and data storage, etc. Content of a data table can be divided into 2 categories: status data and then numbers or codes. The status data, that's the switch that can be open or closed. That's the data that can be a 1 or a 0 to represent the state of a switch, if the switch is open or closed. But the numbers and codes, well, we can't use 1 bit for that. We got to use bytes. And so that can represent the several things in a counter or timer. It can represent the time of a timer or the count of a counter. So we'll get into the details of that. But it takes more than 1 bit to reflect timers and counters in memory. So it's not a status data that we refer to when we talk about timers or counters. We refer to number, data, or codes. And remember, we talked about the difference between a number and a code. Another important concept to understand is this idea of a processor file. A processor file. So a processor file is a collection of what we call program files and data files. So they're kind of paired off, program files and data files, and it contains all the instructions, data, and configuration information pertaining to the user program. So as an example, you can think of it like this. And let me move this up for you. So typical connection of a switch to input image file. Now remember, anything on this side of the input module exists in software. It's virtual. And everything over here, the module itself, and anything to the left is actual hardware. So what we have here is we have a switch. The switch is closed and is connected to this terminal, and as you know, the terminal is mapped to a certain bit position in this image table, in this input image table. Since the switch is closed, there's a 1 there. But notice how this is kind of laid out. This is this data file. So this is actually the way to think about it. And again, it's not actually structured like this in memory. This is just a logical way for us to organize these bits. And so we organize them in these files, data files. So this is the word corresponding to this particular input module. The word, and remember, a word for us is an actual register. A word and the register are the same. And so this is just a way to keep it organized. If I had several input modules, then it corresponds to these other files back here, which again would look like this one. But maybe this is input module 00, and this next card back here, this next input image will be 01, and so forth. So again, this is just for organization. Same with the output. I have a device that's on. Well, the way that got turned on is that in the output image table corresponding, or that's mapped to this terminal, there's a 1 there. And so when the PLC reads that 1, it knows to activate the light. And so the idea here, though, is just to know that the way this is laid out, the logical way it's laid out, the structure in memory, is to think of it as these files. And you'll see that there's a parallel to this and what you see in your PLC. Here's another important idea to understand, and I mentioned this in previous lectures. The PLC, when you use it, runs in a loop. So this slide is actually pretty important. You want to remember this picture, and you want to remember down here the operating cycle. So let's talk about the operating cycle. It consists of 2 parts. There's the I/O scan, and there's a program scan, and this is showing you that this is kind of going in a loop. The I/O scan and the program scan. The I/O scan and the program scan. And the I/O scan records the status data of input devices, energizes output devices that have their associated status bits set to on. So when we do this part of the scan, we're looking to see 2 things. We're looking to see if the switch mapped to a particular terminal is open or closed. If that switch is open, then the input image table is updated to a 0 if it's not already a 0. If the switch is closed, that bit position mapped to that particular screw terminal is changed to a 1 if it's not already a 1. If it's already a 0 or a 1, it'll remain in that particular state. So that's this part, the I/O scan part of the operating cycle. And then there's the program scan. So the program will actually, this part of the operating cycle will look at the program that you wrote and look at the instructions that you use and determine if that rung on the ladder should be true or false. And if it's true, then it's going to update the output image table for that particular bit that's mapped to the output of that particular run to update it to a 1. And if that rung is false, it'll update that particular bit to a 0. So good idea to remember this pictorial, this picture here. And remember that it runs in the loop. We just scan in this circle. It continues and repeats the scan process. And then this little equation here, the operating cycle, consists of the program scan plus the I/O scan. So I will mark the previous slide and then this one. It kind of walks you through it, and I'll show you another picture in the slide after this. So, in the beginning, to start, the PLC reads all the inputs. That is, the switches. It checks to see if the switches are open or closed, or if a sensor is producing data or not producing data. So it looks at the inputs first. Once it looks at the inputs, it updates the input image table. And again, where there's switches, let's talk about switches. If a switch is open, the input image table mapped to that particular terminal is going to record a 0. If the switch is closed, there'll be a 1 put in that bit position. So after the input image table is updated, then the PLC will look at the user program to determine how to respond to the input values. So if I use the examine if closed instruction, it's looking for a 1 at a particular bit position. If it sees a 1, it's true. If it sees a 0, it's false. Whereas the examine if open does the opposite. It's looking for a 0, and if it sees a 0, it's true. If it sees a 1, it's false. So depending on how you structured that, whether you use examine if open or examine if closed instruction, and the type of logic you use. Did you use AND logic on that rung? Did you use OR logic on that rung? Or did you use a combination of AND OR logic on that rung? So depending on all those factors, it's going to determine how to respond to the input. And if the response turns out to make that particular rung true, then the output image table mapped to that particular bit position for the last thing on the rung, which is always a relay coil or some output device, it'll update that bit position in the output image table to a 1. If that rung is false, it'll update that bit position to a 0. And then after that, depending on if there's a 1 or a 0 in that bit position in the output image table, if there's a 0 there, then the output mapped to that bit position will be turned off if it's not already off. If there's a 1 there, the output device mapped to that particular bit position will be turned on if it's not already on. So this is a really, really good slide to know in conjunction with this one. So understand this, and then understand this, and then there's actually a pictorial of this one right here. So here's the first thing we do: read the inputs. We run the program. We look at the program. Now, before I run the program, remember in here, I'm updating the input image table. We run the program based on the values in the input image table, and then we adjust the outputs. Well, in here, before I adjust the outputs, in here, I have to, depending on the results of the program, I got to update the output image table, so what's in here. And then we're going to adjust the outputs. But the point of this thing is it continues to go on this loop. Now, the next couple of slides will really bring this point home, because we can kind of walk through the actual scan process. So, what I have is, again, I have the input module, I have the output module. So anything in between, anything to the right of the input module and to the left of the output module, all of this stuff exists in memory. So this is all virtual stuff. This is hardware, and this is hardware, and anything to the left and to the right of the input module. Anything to the left of the input module is hardware. Anything to the right of the output module is hardware. So let's look at this. First of all, notice I have the input module. I have a input device. It looks like a push button, maybe a normally closed push button. And I have this address. So this screw terminal, I'm going to connect it to this unique address, or it has this unique address that when I use this, it's reflected in the input image table. So there's a cell in the input image table that I can get to by following this address. I can look at this and tell it's a input module. So I'm looking at the input image table. This right here is the number of the table. This is input image table 3, or input module 3. And then this is the bit position. This is the bit position. So I can go to, remember we start with 0. I go over 7, I can get to that particular bit position. So if this is closed in that particular bit position, in this table, remember it looks like an Excel spreadsheet, there'll be a 1 put in that bit position. If this is open, there'll be a 0 put in that bit position. Down here, the user program section of memory. This is the program that you wrote. And what you do, you'll use these instructions. Instruction set, examine if closed, the output energized, examine if open. You use these instructions and logic to determine how you want the program to perform. So here what we've done is we map the examine if closed instruction to this particular bit position using this address. So now it knows to look at that bit position in memory in the input image table. If it sees a 1 there, it's going to perform a certain way. If it sees a 0, it's going to perform another way. We know that this, if it sees a 1, it's going to go true. If it sees a 0, it's going to go false. And then depending on the logic you have on this rung and the instructions you have, whether they're true or false, if there's logic continuity from left to right, if there's a continuous path of truths from left to right, is what we mean by logic continuity, then this final instruction, which is the output energized, will be true. And notice it's mapped to a certain cell or bit position in the output image table. And so what will happen if there's a true there, it'll turn whatever's connected to this output terminal on. If it's false, it'll turn it off if it's not already off. So we'll walk through it. So now the switch is closed. So there's a 1 there. So there's a 1 here. Switch is closed. This is the examine if closed. So it's looking for a 1. It looks here. It sees a 1 there. That makes this rung true. If this rung is true, then the bit position that this is mapped to, there's a 1 there. So the 1 is put there. And if there's a 1 there, then the processor is going to turn on that light, and the light will glow. So if you walk through that process and understand each step, then you do well to understand how the scan process works. Let's say we open the switch. But notice when I open the switch, this didn't change instantaneously. I open the switch and then the processor has to read this. It takes time for any event inside memory. It takes time to happen. So this isn't instantaneous. So this opens, and that's this. We don't know where this is in the scan process, but when this scans back around to look at the state of that switch, it'll update the input image table and put a 0 there. So this changes to 0. And again, it looks like this happened instantaneously, but that changed to 0. But then it takes time to come to this section. This is going to look at that bit. It's examine if closed. It's looking for a 1. If it sees a 1 there, it's true. If it sees a 0, it's false. So now this rung is false. If this is false, as it goes through the scan process, whatever bit position is mapped to this, it's going to change that to a 0. A 0 is held in that cell if it's not already a 0. And then if it's 0, as it continues through the scan process, it then turns that output off. So remember, this does not happen instantaneously. It actually takes time to go through that scan cycle. And that turns out to be an important concept. So, each instruction entered into a program requires a certain amount of time to be executed. That turns out to be important. We'll talk about that in just a second. The amount of time required depends on the instruction. It depends on the logic that you have. It depends on the instruction that you have. If you have a lot of and or logics on a certain amount of rungs, on a certain rung, it takes time to go through that logic. So depending on the number of instructions and the type of logic you have on the rung, that's going to affect the time required to update the input and output image tables. For example, it takes less time for a processor to read the status inputs of a contact than it does to read the accumulated value of a counter or the value of a timer. You would expect that. I mentioned before that timers and counters are more complicated virtual devices. It takes more memory and more words of memory to reflect the counter or timer in memory, and so you would expect it would take longer to read. So this idea of time is going to turn out to be important. I won't say too much about this. You can read this yourself. Just understand that there are two basic patterns, scan patterns used by PLC manufacturers, horizontal and vertical. So your simulation software mimics Allen Bradley. So this will be the one to focus on. But just realize that there's just this other one, vertical. And this slide here kind of takes you through horizontal scanning. It makes sense. We read. It's kind of like we read. We read from left to right. So we read from left to right. So we'll scan this one from left to right. We'll scan this from left to right. And we'll scan this from left to right. So this shows you the scan pattern. And then it'll just keep repeating that. It'll keep repeating that over and over and over again. Now I mentioned the importance of scan time. And so mark this slide if you have your printouts. I'll pause for a second and give you a second to read this. This turns out to be pretty important. Alright, so this is important. If you ever have to connect up or work on a PLC system, this idea of scan time. So it's understood then that it takes time to go through the whole scan operating cycle. It takes time to look at the status of a switch. It takes time to update the input image table, and then to look at your logic, and then for that logic to react by making the rung true or false, and then to update the output image table, and then to turn on or off some device. It doesn't happen instantaneously. It takes time to do that. And the more complicated the device, that is, if you the input instruction, if you're using a timer or counter instead of a regular coil or contact, and the more logic you have on the rung, the longer this process is going to take. So, PLC scan time. How fast the controller can react to changes in the input. Scan time varies with program content and length. So it varies with how long it is. A longer program will have a longer scan time. And program contents, as I said, if you have a lot of and or logic on a rung, it's going to take longer for the scan time for the scan to go through that particular rung. The time required to make a single scan can vary from 1 millisecond to 20 milliseconds, which seems still to be pretty fast, but it is possible to have signals change pretty fast. So it can change outside of this. If it changes in 25 milliseconds, then there might be an issue. If a controller has to react to an input signal that changes states twice during the scan time, it is possible that the PLC will never be able to detect this change. So here's an example. If it takes 8 milliseconds for the CPU to scan a program, and the input contact is opening and closing every 4 milliseconds, the program may not respond to the contact changing state. The CPU will detect the change if it occurs during the update of the input image table file, but the CPU will not be able to respond to every change. So this part of this paragraph of this slide is very important. If my switch contacts, if they're changing, if they're opening and closing faster than the scan time, then there's going to be an issue. And if you think about that, that makes common sense. So the time taken to scan the user program is also dependent on the clock frequency of the microprocessor. The higher the clock frequency, the faster the scan rate. And I forgot to mention that, but that goes back to the first week of class. We talked about signals. We talked about periodic signals and non-periodic signals. Periodic signals, that came from the circuitry called a clock, which I call the heart of a digital system. And the non-periodic signals is the data, the zeros and ones that you're moving back and forth. Nothing in a digital device can move faster than the clock. And so you would expect the PLC scan time to be affected by the clock speed. The higher the clock speed, the faster the scan is allowed to be. So that's the end of this video. If you guys have any questions or comments over anything in the video, if I wasn't clear on something or you need more explanation, please send me a text. I'll see you soon.